So hello everyone, good evenings, and thank you for being there, and welcome to this webinar about digital twins. My name is Vincent Trofaz. I'm an industrial engineer, so I did electrical and automation engineering in the industry during 7 years, and now I'm a research engineer for the CECOTP, so the research center of Province de Liège, and I'm working with the HEPL on a project called EMR Digital Twin Academy. And I'm doing this project with the help of Rodrigue Rollor, who is teaching industrial engineering at the HEPL. So here is our timetable for today. We'll start by presenting the project background and why we are here today. Then we will introduce the notion of digital twins and see how they can help us in our life of engineers. And so if you have any question, we will be glad to answer you at the end of the presentation. So we are here today to talk about digital twins, and this in the context of the EMR Digital Twin Academy project. So what is this Digital Twin Academy? This is a European project for the Région Meuse. This project is financed by Interrect, which is a European institution, and the project is a consortium of 11 partners around the area. So we have some partners in Liège, like Elmo, the University of Liège, and we also have different partners in Belgium, in Germany, and in the Netherlands. So what's the purpose of this project? There is two main objectives. First one is to elevate the general knowledge of expertise regarding the digital twins. For that, there will be different work packages. The first one is to organize workshops, webinars, and so on. This is what we are doing right now. And the second part is to create a platform of online learning modules. So the platform is already available with 20 basic knowledge modules, and in 2023, there will be another 20 modules with a more advanced level. And the second main objective of this Digital Twin Academy is to realize digital twins with business partners. So now let's talk a bit about Industry 4.0 and digital twins. So Industry 4.0 is maybe something you have already heard. We know it what we can call the fourth industrial revolution. For the quick history, the first revolution was about mechanization and steam power. Then came the second revolution with the electricity and the start of the mass production. The third revolution was about the arrival of computers and automation. And now we are in the Industry 4.0. So this Industry 4.0 put a lot of interest on the data. It's focused on the interconnectivity, so everything is connected and talk together, a smarter automation, machine learning with artificial intelligence, real-time data. So we have direct access to all the information we need and when we want it. And cyber physical systems, so that system that merge the real world to the digital world. And thanks to all those technologies, we can now have digital twins. And in order to introduce those digital twins, we'll have a bit of history of the simulation. So in the 1960 years, we started to use computer simulation for very specific usage, but it was still very expensive at that time. In the ITs, the computers are more present and less expensive, so the simulations becomes more accessible. In the 90s appears the first 3D simulation, and in the year 2000, we've seen a arrival of more complex multi-system simulation. But still, there was a difference between simulation and reality. But today, we have the possibilities to have computation with better performance. Every year, the material is better than the year before. and computation performance always improves. It's now possible to collect data with IoT, Internet of Things. We have access to real-time data easier than ever. We have the data science that gives us the possibility to extract knowledge from all the data we collect. We have artificial intelligence and other key technologies. And with all those technologies, it allows us to interact in real time between the reality and the digital model. Let's talk now about the origins of the digital twin. So first, in the 70s, NASA used a physical twin for the spaceship to simulate operation conditions, and that was for training purpose. So the crew was able to train on the physical twin, so still on Earth, and face different scenarios and get ready for any problems. So if any situation issues occur in the space, they would know what to do because they already simulate those things on the physical twin. Later, this spaceship twin becomes digital, and in 2003, the term digital twin was first used still by the NASA. And since then, the first application of digital twin were used for aerospace application. And since, let's say, 2015, we can say that this concept has reached the industry and all other areas too, as we will see later today. So how can we define a digital twin? There is no exact definition. People are still debating about it. But one of the most common is the following one. A digital twin is the virtual representation of a physical system. So this virtual representation is a tool that can be used for a lot of things. It can help to detect problems. So if we detect problems on the digital twin, we can avoid them on the real object. On this digital twin, we can run tests and simulations. So if we can do all those things on the digital twin, we have more freedom for those tests than on the physical system because we're in the virtual world. There is no constraint in disponibility or feasibility. There is no risk because we're in the virtual world. We will not break anything or damage anything. And you can also get real-time data analysis, and with artificial intelligence, this can be used as a help to take decision, to make prediction. And since the beginning, the digital twin has been associated to the product lifecycle management, and it can be used in every step. So first, we will try to understand what is this table. So we can see on the left, we have the two main categories, the type and the instance. So if we take the example of a car, we can say that the type is, for example, a Volkswagen Golf, and the instance are all the Volkswagen Golf that are produced. So if tomorrow you go to your car shop and you buy a Golf, you will buy an instance of the type Golf. So in the type, we can find two categories, the development of the product. So we can say it's all the engineering and so on. And there is a maintenance usage. For example, those are the maintenance instructions for that product. And in the instance, we have the production. So this is the production process of the product. And then there is the maintenance usage. This is the maintenance usage done by the owner of the product of the instance. Here we can see it on a different view. We have the type, so which is used here as a prototype for the development. Then we have the instance that are created during the production. And at the end, we have the final client that use the product. And also feedback can be given back to the development to improve the product. So now let's see how the digital twins can be used in those different life cycle. So usage of the digital twin in the development process is a great help. Working in the digital environment costs less than working in the real environment, of course. You can build a virtual prototype and realize all the different tests and simulations on it. You can use virtual reality or augmented reality to have an immersive and interactive experience with the digital twin. And it can also be used to understand what's not working on the instance produced. In a production environment, the digital twins helps to optimize the material flux, the information. It helps to improve the planification, identify bottleneck, and have a full traceability. And during operation, the digital twin will help to optimize the lifetime of the object, for example, with predictive maintenance. It can also provide feedback to the design phase to improve it. And at the end of the life, the twin can help to guide the actions to take. So can the equipment be reused, be reconditioned, be recycled, or scrapped? So we can see that the digital twin can be used all along the product life cycle. And a digital twin can have different level of evolution, of maturity. In the first step, we have a digital model, a digital prototype, and we can feed this model with offline data and run simulation with it or monitor the state. In a second step, we can collect data automatically in real time and feed the digital twin with it. So the model gets directly the data from the physical world, and we have then what we call a digital shadow. It can be used for supervision, can be used also for optimization of the physical twin. In a third step, we will say the digital twin uses a bit of artificial intelligence, and it can control some parts on the physical twin. With an improved layer of artificial intelligence, we get a smarter twin. It can learn from the data, from the physical and the virtual environment. It can make simulation by itself, and it can help us and recommend the user to take decisions. And at the final step, we have what we can call an autonomous twin. That one will be able to take decision itself and control completely the physical product. Now we will see more in details how the digital twin can help us in the different product life cycles. So for the development, production, and operation. And we will start with the development. So here we have what we can call the traditional process of development that we can divide in three main phases. First one would be the analyze and concept, let's say. So we have a request for a new product, a new machine to perform a specific purpose. So what we need to do at this step is understand the requirement. What is it supposed to do? How? It's important to understand that to consider the possible solution. And then we will choose what seems the best option out of different possible solutions. Then will come the engineering. So the phase is all the conception and detail work. How is the solution is implemented? How is the product going to be manufactured? How is the machine going to work? And finally, we have the last step, the production of the object, the manufacturing or the commissioning of the product, the machine. So here we put every pieces together and we test if it fulfills its purpose, if all the functions are working as expected. And this step can be a bit tricky because there is a lot of different problems that can happen. For smart products or machines, for example, there's a lot of different technologies implied, and the merging of all those technologies can create issues that were not foreseen. It Can be mechanical issues, electrical or electronic problems, software issues too that happen a lot. And we need to test all those functions, fix the problems, and discuss time and money. So sometimes first we build a prototype, and the test can be performed on the prototype. But build a prototype costs also time and money, and you need to build it. This takes times too. And then if the tests are not good, you need again time to modify it. So back to engineering, you modify. And then again, time to manufacture the modification and so on. So you have an iteration loop until the product is good. So it's interesting when you need to produce a lot of the same product afterwards. But for example, if you do a one-time machine or a one-time product, for example, building a prototype will not be relevant. Cost will be a loss. And this is why we are talking now about digital twins. And as we will see, they can help us in this process by building a virtual prototype. So now the virtual prototypes are used in tests instead of physical prototypes. So it's less expensive to develop. And either you design or test a new product. A virtual prototype will be a 3D model that will replace the physical object in the commissioning, test, and validation. So it can be used to predict performance or to find defects during the design phase. So this is both. This is again in both time and money. The virtual prototyping with models and 3D simulation will help us to accelerate the design phase, and it will reduce the number of physical tests and the number of iterations to manufacture and so on for the prototypes. So with that virtual prototype, it's possible to simulate flows and activities, can test different layouts for a machine, for a production center. And then when you do it, when you build it, you have directly the good one. You can test different scenarios. So if you have different possible solutions in mind, you can test all of them in the virtual prototype and then choose the best one. If you don't have that, you will not build, for example, 5 different prototypes to see which one is the best. It will cost too much. But here, without even to build anything, we can test 5 different virtual prototype. And with this one, you will also be able to detect failures, defects, mistakes, and everything you will detect and fix in the virtual prototype. You don't need to do anymore on the real object. So here we can have a demo, small demo of a virtual prototype. So this is a pickup station that will collect some elements from a stock and drop them on a moving car. So in this kind of virtual prototype, we can already test all the automation, all the positions. We can check if no collisions happen and so on. So when we start to build the machines, most of the tests are already done. And the machine is normally almost ready to be used. So create products in the virtual environment is a new way of working. It will accelerate the design phase. You don't have the iteration of building a real prototype, like test them, then go back to design, update it, and so on and so on. Here you can do all those steps in the virtual environment, so it will save you time. It stimulates innovation too, because realizing a prototype is not a problem anymore. You can try different things. You would maybe not try with a real prototype. So it gives you more place for innovation and imagination. The development costs are reduced because you don't need to build physical prototype and spend that time testing them. And the same way, the time to market is improved because you don't need all the time to build prototype. And at the end, you also have a better reliability because you have better developed products thanks to the digital twin. And also it improves what we call the concurrent engineering, which means that the different team of engineers work together on the virtual prototype, while in the past they more tend to work each one in their corner. So that's it for the development part. Now let's talk a bit about the production and how it can be improved with the digital twins. So it can be really useful to have a digital twin of your production environment. With the digital twin of your production center, you can monitor it, so you can know how the machines are running, which machines are busy, which machines are not, which machines are down, have problems. So this gives you a good idea of how the things are running. You can see some important machine parameters and some KPI directly in one point. So if some problems occurs in the production, for example, a machine is down, the digital twin can automatically redirect the production on a different machine. So you are not stopped in your production. And when the machine is back, the digital twin will reassign the production to that machine. So a smart digital twin can directly pilot the plant based on a lot of information and simulation. And digital twin can also help for the planification and help to optimize the production. So for here directly on a process, you can have a digital twin of your process, and you can do all sorts of tests on this digital twin, because most of the time the production tools, equipment, they are busy running, producing, so you don't really have the occasion to realize tests on them. Or maybe you don't dare to make some tests because it could be critical. It could be dangerous or lead to scrap product. That would be a waste. And with a digital twin, you can simulate all those things without those problems, because everything again is done in the virtual environment. So with the twin, you can a bit play with process parameters to see the different results. You can try simulations with different material characteristics. You can try different environment parameters like temperatures if they have some influence. And all those simulations can bring you knowledge to help you improve your process. So digital twin of instance. So when we produce the instances, we can create the digital twins. By this, we mean to create a digital replica that will represent all the manufacturing conditions of each final product. So if we have a full traceability of a process, so from the start, we record for each operation which raw material is used, which are the parameters of the production equipment, maybe the parameter of the room, temperature, humidity, if they have influence on the process. If we do quality control, we can also record the results. And so at the end of the process, we associate all those data to the final product, and we can have what we call its digital passport. So it's the digital twin of the production process of that product. So at the end, you know everything that happened in the production. And later on, maybe we can find a defect on this object. And thanks to this digital passport, we can investigate on all the parameters of production on that day. And we can understand why this problem happened, and we can avoid it to happen later. And also, maybe we can recall other products that were produced in the same batch, because probably they have the same defect. And when you start to record all those things, you also record where are the components in the production center. So you can know how long and where some raw materials are stored before they are used. You can also know how materials are moving, are they always in movement? Maybe there are some steps of the process where some components don't move. So that can help you to identify the material flux in the production center, identify the bottlenecks too. And with all those data, you have better information on how the materials and production move. You have then a kind of digital twin of your logistic, and this can help you to improve and optimize all the material movement and conditioning in your production plant. Quality is also an important aspect in production. So if the product doesn't meet the required quality, it cannot be sold. So reduce the number of quality defects is very important. Digital twins are being developed for quality control as well. So with the help of artificial intelligence, the digital twin of the process can make links between some parameters and quality. And with that, by following those data, it can predict in advance that a drop in quality will occur, for example, and by alerting us, by alerting the operator on time, the problem can be solved before the quality problem appears, and then we reduce the number of waste due to quality. This is also very important. Yes. Today, the question of energy is more and more important. Every effort to try to reduce energy consumption should be done. And on the same way, we're always trying to optimize the production costs. So with a digital twin, you can improve those 2 points. With artificial intelligence, a digital twin can predict the energy consumption of the production. So depending on the batch to produce, the digital twin can reorganize the production planning to optimize the energy consumption. For example, it can prioritize the, let's say, most energy demanding production batch during the day when, for example, we have solar panel that can produce electricity, and it will keep the less energy demanding process for the night. So it can adapt the production planning according to all those parameters that will have influence on the energy consumption, like, for example, the weather forecast. And in the same way, the same way will apply to produce when the energy cost is the more beneficial. So this allows to reduce the cost. So today data is really an important tool. It becomes really more and more important. The key is to have the right data to the right person at the right time. This is not always easy, especially on remote equipment. And the capacity of visualization of the equipment with the digital twin is particularly interesting when the equipment is far removed or in a difficult environment. So the digital twin will make the data accessible and can provide data that you can't measure directly on the physical object, for example. And all those data that were used to be difficult to obtain are now there, and they can help us to monitor or process our equipment. And the digital twin can also be used for training, to train people. So if you install a new production line in your plant, you can already train on its digital twin. So when the machine is ready to produce, you are also ready to use it without losing time getting used to this new equipment. You can train new operators on that digital twin. So when they arrive on the equipment, they are used to it and they know how to use it. And the training happens in a virtual environment, which is a safe environment where no accident can occur. There are also some specific tasks that can be tricky and that you don't realize often, maybe once a year. So maybe you can realize them on the digital twin first to be sure to do it properly before you do it on the real machine. So that's it for the production part. And now we'll talk about the operation with digital twins. So here by operation, we mean good usage of the equipment, which also mean we need to maintain that equipment to a good state. So here we have a definitions of maintenance. So it would be all the actions which have the objective of retaining or restoring an item in or to a state in which it can perform its required function. The actions include the combination of all technical and corresponding administrative, managerial, and supervision actions. So we can say that maintenance includes the action of troubleshooting, repair, setting, control, verification of material equipment. And as you already probably know, there are two main categories of maintenance: corrective maintenance and preventive maintenance. So for the corrective maintenance, this one is done after the failures occurs. So we have an equipment breakdown or it doesn't function properly anymore. And the goal of the corrective maintenance will be to restore the equipment to a condition where it can perform its function. The corrective maintenance can also be split into subcategories. So we have the curative maintenance, which is a long-lasting repair that will restore the equipment to its initial state. And there is also the palliative maintenance. In this case, this will be a temporary repair that will allow to provide all or part of the required function, but that palliative maintenance will need to be followed by a curative maintenance later. So we can say that corrective maintenance is based on the reaction to the failure, which means the problem already happened and the equipment is down. And on the other side, the second category, preventive maintenance, that one consists of acting on the equipment before it fails. And this prevents any breakdown. So ideally, nothing will break down, and the goal is no failure between two planned maintenance services. And we can do this by replacing the components before they fail. It can be split in three subcategories. We have the plant maintenance, which is done systematically. So according to a schedule, a fixed interval, maybe every 2 months, for example, or according to a periodicity, like the number of hours of operation or the number of units produced. Then we have the condition-based maintenance. So that one is those based on inspections or data coming from sensor. So those data give us the state of the equipment, and the goal is to try to maintain the equipment at the right time. So not too early because the equipment is still able to perform, and not too late because there would be a failure. And finally, there is also the predictive maintenance. So this one is based on the evolution of the state of the equipment. So the goal here is to estimate when the equipment will break down, and so estimate when the maintenance should be performed. So for this, we will use sensors to monitor the equipment's parameter. And with machine learning and historical data, we will continuously evaluate the equipment status and predict when the failure will happen. So let's see now how the digital twins can help us with the maintenance, and here with the corrective maintenance, our first category. So in case of a breakdown, what we need to do is to react as fast as possible to restore the equipment, because every equipment down cannot produce. If it cannot produce, we lose money. And for that, the digital twin can help to diagnose the root cause of the problem. It can provide also a 3D representation of the faulty equipment without having to dismantle it. When there is a breakdown, we also need to access documentation, like technical documents, datasheet, technical notes, historic data, everything you can imagine. And it can happen that sometimes those documents are not all stored in the same place. So here we can integrate all those documents in the digital twin in a single point. And this makes it easy to get all the necessary information. We can even use augmented reality to help us to directly get access to that information. So for example, with a tablet or a smartphone, we scan a QR code on the equipment, and it will give us directly access to the documentation we need. The technicians can also use that augmented reality to be guided step by step in the operations to do. So we make sure they follow the procedure and they make no mistake. This can help for complicated tasks. And even better, with connected glasses and digital twins, we can have assistance of a remote expert. So it can help us and guide the technicians through remote diagnostic. So the expert is not on site, but he can access remotely to all the information from the digital twin. And so it means that they don't need to come on site, but they can still assist, which will save time and of course money. So here in the case of corrective maintenance, the digital twin can help us to react faster and more efficiently in case of an equipment failure. For the preventive maintenance now. So in a first step, the digital twin will collect data, and it's possible to know the status of the equipment with those data. It's possible to make condition-based maintenance by following critical data of an equipment. So for example, speed, temperature, vibration, and we can set a threshold. So if the data reaches a threshold, we can have an alert that will inform us that we should make the maintenance now. In the second step, with those data, it's possible to run simulations. With the digital twin, you can replicate the operation conditions, and then it's possible to predict failures. And in a third step, with the help of artificial intelligence, the predictive maintenance can be used. So the digital twin will predict itself the failures and identify the cause of it. So it can estimate the remaining lifetime of an equipment. And if the digital twin knows also the planification, when the machine is supposed to produce and so on, it can even recommend us a time period for the intervention, and it can even order by itself the necessary parts. So in this case, it can be very useful. So that's it for the product lifecycle management part. And now for the last part, we can talk a bit about the different business area where the digital twin can be used. So as we have seen early, the concept of digital twin was born in the aerospace, in the NASA. So in those areas, the technologies are more mature and the means are more important. There is also a lot of application in the production environment because it's rich in data. There is a lot of controllers, sensors, connected equipment. There is also a lot of competitions between manufacturers, and every technological advantage can have a huge impact. But digital twins don't stop there, and they cover more and more fields, as we will see now. So as we said, aerospace, it was first used by NASA. They are still using it for the spaceship, so it receives real-time data. It can help to optimize the performance and predict fault, and it will help the engineers on the ground to understand the problems occurring in the space, so they can propose solutions. Also, airplane manufacturers notice that after preventive maintenance, a lot of replaced equipment are still in good conditions. And they also notice that some equipment passed the inspection test while being defective. So they started to use digital twin for predictive maintenance. So airplanes are equipped with continuous monitoring system, and this helped them to predict failures, to predict when the maintenance will be necessary. And with that, they can optimize the maintenance planning of the airplanes. And airplanes are not the only mean of transport that use digital twins. So for example, digital twins start to spread in the transport. Some fleet companies are creating digital twins of the vehicles to optimize the maintenance and to optimize the running time. For example, for truck fleets, the tire data are monitored. So a lot of data are collected from the tires, the wear, the pressure, the temperature, and they're analyzed to evaluate the status of the tire to be able to change it before it breaks on the road. The goal here is to avoid a situation with the immobilized vehicle. Some companies also create virtual environment to train autonomous car. So the cars can travel millions of kilometers in this virtual environment. They can simulate a big amount of car, simulate interaction between them. So there is a lot to learn out of it. And this is really easier to do in the virtual environment than launching thousands of autonomous cars in the street, in the real world, which will be a big problem. We also have train manufacturers that develop digital twins to improve the maintenance of the train. And also on the boat transportation, the digital twins being created to collect real-time data, analyze them. It will help to detect degradation in the equipment. So this will be done to avoid failures and to increase the reliability and the availability of those boats. So in the energy field, so usually equipment are far from monitoring stations. Digital twin allow to operate them remotely and to improve the reliability of those equipment. For example, for wind turbines, the digital twins can be really useful, especially for offshore wind farms. So the digital twin can be used to monitor them remotely and predict the residual lifetime of components. The maintenance is done then only when necessary. So the costs are lower because sending the staff offshore costs a lot, and the reliability is increased, and so is the production of electricity. The same applies to the offshore petrol platform. A digital twin for such platform can reduce the number of staff present on the platform by optimizing the operations of the platform. We can also digitalize power grid. So this digital twin will help for the planification and the operations. It will allow to automate manual operations without having to travel to the remote site, for example. It improves the usage of data and gives a help for decision. In the power plants, it's the same than for the production. It will help to monitor, optimize, and increase the reliability. In the water treatment, there is also a lot of remote installation to monitor and drive remotely. The digital twins can help for that. And there are even some digital twins that are being developed to detect the water leakage in the network. So this will increase the network safety and maintain the service. So smart city becomes a popular term. So they can have an interest in digital twin to improve the traffic, the energy, the communication, the waste management, and so on. And one of the objectives is to improve the carbon footprint. Digital twins can also be used to develop new buildings. So a lot of things can be simulated in advance in a virtual environment to build a more efficient building. Digital twin can also be created during the construction and updated daily with the advancements. So the digital twin is updated according to how it is being built in the reality. So we can compare the reality and what was foreseen, the study. And if there are differences, the digital twin can predict if issues can happen with this. And digital twins can also be used in building to control the heating, ventilations, elevators, and so on. So like a production environment, it will give information to monitor and optimize the consumptions. And it will also help the maintenance when we have some equipment down. We also have digital twin in the health area. So a lot of researches are being made on the simulation of the human body. So we can simulate diseases and use those digital models can be used to train doctors to diagnose on the virtual bodies. Some heart digital twins have been realized too. So heart from patients to do simulation. So this can be done to know when to act on the patient and how. So you can try different approach on the twin, surgery, treatment, and so on. And then you can choose the best solution for the patient. Another advantage of using digital twin would be to test new medicines on virtual model, so human digital twins. And this would allow to reduce the test on the animals, for example. And you can also realize digital twin of hospitals to improve the planning of the rooms, the staff, and so on. Agriculture. So if we have a digital twin of our plantation, we can simulate and predict how they will grow according to the weather forecast, the fertilizers, the watering, and so on. So the digital twin can guide us on those actions and how to optimize our plantation to have the better harvest we can get. For a big farm, the digital twins on the machine fleet can also be used to monitor and maintain the machine. And on animals, it can help with animals. For example, when you collect the milk from the cows, the milk can be directly analyzed, and based on the quantity and the quality, you can also help to monitor on the health of the cow. For example, if she's normal, if there is a drop of quantity for the past day, maybe there is a problem with that specific cow. So here we are at the conclusion. So this term digital twin is more and more used, more and more popular. On my personal opinion, I would not define it as a new technology, but as a tool that is built thanks to the new technologies. So it's an evolution of what has been done so far. So if you remember the part on the different step of evolution of the digital twin, we noticed that the first step, like digital model for simulation or digital shadows, those things already exist. Some company already have them since long. But today the tools become more and more performant. We also have new key technologies like data science, IoT, and all those new technologies coming with Industry 4.0 would help us to go to the next steps of digital twins. So to have more and more possibilities in the futures, there's still more to develop, and we can get later evolved digital twins. So as I said, there were digital twins were already among us before this term started to be popular, but we didn't name them digital twins yet. And as I just said, there's still a lot of things that we can develop about that subject, and that we are only at the beginning of it. We are just at the top of the iceberg. Also, a common mistake that I have, not really a mistake, but a lot of people still think that a digital twin is a 3D representation of the object. So of course it can be, as we have seen. But if we come back to the definition, it's a virtual representation of a physical system. So it's not necessarily a 3D representation with all the details. It can be a simplified 3D representation with just a few relevant data, or it can even just be a dashboard. The way of representing it, it's not the most important. The important point here is the information it gives back to us. And what is also important is the model behind it that replicates the physical system. So to conclude, we can say that digital twins are helping and will help us in the future in a lot of cases. Either it is for the development, for the production, maintenance, that it is for energy, for cities, transportation, industry. We have seen that there is a lot of possible application. And there is still a lot of development to be done, a lot to learn about it. But definitely those digital twins will bring an added value to our daily life. So now it's the question time. So if you have questions, don't hesitate, and you can ask a question in French if you don't feel comfortable with English, it's okay. I see there was some question in the chat.
Sorry, can you hear me?
Yes, I can hear you.
Oh, that's great. Okay, I already raised my hand and I put some questions in the chat as well.
Yeah, I didn't see, sorry.
Doesn't matter.
I was busy.
Thank you very much for your presentation. Very nice. Yeah, the first thing is actually, it's a nice example you showed for the manufacturing industry. But how is this in the process industry? Yeah, for example, the chemical industry where I'm coming from. We're also looking at digital twins and well, maybe digital twin of an asset or digital twin of a whole plant. But I don't see many examples actually coming from the process industry. So how is it established in the process industry, this concept of digital twin?
Unfortunately, so far we have a lot of concept that could be done, but of course the people that are realizing those things are not sharing it with the outside world, so it's difficult to know today what is being done. But of course, for the process of chemicals and so on, those are not easy things to simulate, and I guess you need to build a strong algorithm behind that to be able to digitalize those processes.
Yeah, but that's something we can do. That's not new. That this has been done, but and that is also related to the second question. I have data integration, because if you speak about the concept of a digital twin, it's related to data, but data integration, I think it's very, very important to get this running, because if you have data on different locations distributed all over systems, you will never manage to well, maybe you may create digital twins, but they're all, let's say, living apart and not really communicating with each other, because that is at some point that's something you really want, that you have, let's say, a digital twin of your plant, but also then digital twins of your assets, which then communicate and form the bigger digital twin.
Yes, that's the challenge, is to you have different digital twin of different assets, but of course they need to communicate together, and the goal would be to have a web of digital twins all communicating together, and here the data is very important, and this is why today with the data science we can better use the data. We have better algorithm to get knowledge out of data and so on.
But I missed the word data integration. How you make sure that you integrate all that data?
Sorry, I didn't understand clearly.
So I mean, actually, it's not that easy to have data integration, because if you buy an asset, usually the asset supplier also has some kind of software sensors in the asset, which then do not communicate with the other asset, which also has sensors and maybe software from the other vendor. So then you have kind of vendor lock-ins there where you don't have standards of data communication, and then you already have a messy system already. So how do you ensure that your providers and suppliers actually well, look a step forward and look at actually to the point of data integration.
Yeah, here it's a problem that has always been existing in the industry. It's every manufacturer works in his corner and try with this proprietary data. And yes, for all the technologies coming and so on, it should be working in a standard way to allow us to extract data as we want. But yeah, I understand
your PLC
you.
supports the OPC UA protocols. You can communicate and transfer your data with, by example, CAP server. I don't know if you know this solution.
What was that kind of server that you mentioned? I could not understand.
CAP server.
It's an OPC server.
It permits to communicate in OPC UA. It's a communication protocol, which is supported by all the new PLC and sensor. So it's the new standard, more or less.
Yeah, but you have, of course, you have this greenfield and brownfield, and so if you have a brownfield factory, and you have these old assets, they do not speak any OPC UA. If you're lucky, they speak Modbus, and then well, you can start with that. But anyway, I see your point. The standardization is quite important, and it's also quite a thing I'm missing in this presentation, that you need data integration and you need also kind of a standardization.
Of course.
CAP server support a lot of protocol of communication, Modbus, Profibus, CANopen, and after that you can connect to the server and speak in OPC UA. So it's a way to gather all the information in your database.
And of course, today we also have the IoT sensors that allow us to not have this problem of protocols communication anymore. But of course, it's new equipment you need to buy and install. It's always difficult to use new technologies with the past product we already have. There is always that problem. Any other questions? Comments?
Will you tell us more about the next step of the project? For example, the Cyber Factory?
Yes, so as I said in the beginning of the presentation about the Digital Twin Academy, there are two main purposes, and the second one was to create digital twin with business partner. So in our case, with the CECOTP and HTPL, we work with Technifuture in Liège. So they have a CEP factory. Those are small faster stations that produce kind of smartphones with all the Industry 4.0 technologies on it. And we will realize digital twins of those stations. So in the first time, it will be a kind of development virtual prototype. So we will use the software Siemens NX to build a virtual prototype of it that can be used as a demonstrator of the technology. And we are also thinking of how we can create other digital twins, for example, for the production monitoring and so on. We were looking for pilot project with the process industry at the beginning of the project with all the different partners, but now every partner is already its own project. So we cannot take new ones anymore, I think. Reply to your question.
And could you tell us more about the future workshop about Siemens NX, maybe?
Yes, so in February, in the case of the digital twin class that Mr. Rollo is giving, we will organize a small workshop about Siemens NX. So we will do a bit of basics and how to create a virtual prototype from a station. So we will do small exercise, move some components and so on. It's really interesting. Last year, the students, we had kind of the same and students liked it. And Willem, sometimes with the consortium of the EMEA Digital Academy, we're organizing kind of events where we invite industrial people. So maybe if you are available on that day, you can come and to discover a bit more of what we are doing. And maybe by networking, you can meet people that would be interesting with your project. So you can send me an email at the end if you want, and I will invite you to the next ones.
Sorry, I did you direct me? No, was it directed to me?
Yeah, I was talking to you. So
okay. No. Well, I'm very into it. So if possible, yes, I'm very interested in this.
We have different partners working on different kind of use case. So maybe there is a use case that will more fit to what you are doing, and you could get interest into that.
Yeah, I'll send you an email. Thank you very much for this invitation.
You're welcome.
Very appreciated.
No more question? Should we end the meeting?
Yes, I think. Thank you.
Thank you.
Thank you everyone for attending. And have a good evening and have a nice end of years and holidays.
You too.
You too. Thank you. Bye-bye.
Bye.
Bye-bye.
Bye.